Why does satellite-based traffic management matters for green mobility? Better freight coordination. Efficient communication and management of the fleet. Optimizes goods distribution. Increases efficiency and lowers environmental impact. Empowering citizens for climate action. Sensors in different geographies and climatic zones complement knowledge and improve accuracy of information. On use of resources. For weather forecast. Communities can share information using data space-based applications. United citizens-based climate action can lower CO2 emissions. On energy and water needs. To link citizens to science. How can satellites help precise farming? Geographic Information Systems, GIS, provide near real-time data. Support management of crop types, quickly and accurately. Help identify soil composition and fertility for seasonal predictions. Disease monitoring, irrigation needs and growth patterns. Assist on best time to harvest and help producing high-quality food. Why does satellite-based traffic management matters for green mobility? Better freight coordination. Efficient communication and management of the fleet. Optimizes goods distribution. Increases efficiency and lowers environmental impact. Empowering citizens for climate action. Sensors in different geographies and climatic zones complement knowledge and improve accuracy of information. On use of resources. For weather forecast. Communities can share information using data space-based applications. United citizens-based climate action can lower CO2 emissions. On energy and water needs. To link citizens to science. How can satellites help precise farming? Geographic Information Systems, GIS, provide near real-time data. Support management of crop types, quickly and accurately. Help identify soil composition and fertility for seasonal predictions. Disease monitoring, irrigation needs and growth patterns. Assist on best time to harvest and help producing high-quality food.
if this is the first time, buckle your seatbelt because we have a journey to space to do. Yesterday, we had almost 800 people in the audience, an amazing number for a crucial subject. And we are starting a day of experiences, discovers, and ideas. This conference for climate change from space is a field to discuss what can we do from space and out of space to mitigate the climate changes. And now, an amazing image, once again, with these doors open, we can see live what the astronauts can see from up there, from space. This is the image live from the International Space Station, and it's incredible to wake up and see this, I don't know, overwhelming image from the Earth. And today it's Earth Day, so therefore this is the perfect conference, the perfect day to talk about the future of the Earth and the climate changes. Exquisite professionals, investigators and investors were here yesterday and will be here today, and we'll have time to pay attention to your questions and doubts. Remember, just go to the chat box and share them with us. And now, time to start today's first panel, Resilience to Environment Changes, Adaptation and Mitigation. We want to know the role of international structures to help progress with global measures in mitigating adaptation to environmental changes. I think that we had on our timetable, in our schedule, Philippe Tulkens. I don't think that he's ready because we have a technical problem with the audio. So I'm going to ask help to anticipate the speaker, Kirsten Dunlop. I think that she's already with us to share her thoughts and also her knowledge. Kirsten is Chief Executive Officer, Climate-KIC. Kirsten's career spans academia, consulting, banking, insurance, strategy, design, innovation, and leadership. Oh God, I'm already tired to say all the things you do. We are very glad to have you with us, Kirsten.
Hello.
Hello and welcome. Can you hear me, Kirsten?
Now I can, but I haven't heard you before.
Oh, no. I said great things about you and about your career. I was saying to the audience all the things you do. You're an amazing woman and an amazing career professional. So therefore, I was telling all the people what can we expect from you, and now we want to hear you about this team.
Thank you very much indeed. My apologies. Okay, so good morning, everybody. My name is Kirsten. I will not step into that. I'm almost scared of what has been said. So let me step straight into what it is that Climate-KIC, EIT Climate-KIC, has been doing in the space of climate adaptation and the use of space information and the building of skills to make use of space information to build up the climate services market and to build up climate services as a solution for European adaptation to climate change, and for the relationship between adaptation and mitigation, and the relevance and importance of that in relationship to the mission on climate adaptation, to the context of Horizon Europe, and to the EU adaptation strategy. Can I just check, because it is slightly strange, whether the sound is working? Can you hear me okay?
Yes, we can. Perfectly.
Okay. Perfect. So EIT Climate-KIC, to give it very, very brief words of introduction, we are a public-private partnership. We are focused on innovation for climate change, addressing adaptation as well as decarbonisation and mitigation. We are funded by the European Institute of Innovation Technology and by a number of other public and private funders. And we have been closely involved since the beginnings with space information, with the Earth view, with information from satellites, and with a combination of that and ground truthing. We're involved with the Copernicus program, particularly in building skills to understand and use and build the market of climate services. We've been instrumental in working in the Marco program to set the enabling conditions up for a climate services observatory. And we have supported and developed a number of innovative solutions that draw on information from space, from satellites, and from ground truthing, and the combination of what we can see to address needs in terms of financial markets, disclosure, and divestment in agricultural practices and protection, both insurance, but also climate-smart agricultural practices that are supported by real-time information. In forestry, okay, now I'm getting an echo.
Hear you perfectly. Sure. Yes.
Okay. No, so I'm.
You're having feedback with your
Yeah,
audio.
I can hear myself. Can we? It wasn't like that. Can we do anything I can do to stop that? I'll try keep. Okay, I'll try. It's hard to speak when you hear yourself speaking on top of yourself. So in forestry preservation and in reforestation, flood risk management, supply chain protection, land use and landscape regeneration. So quite a number of startups from something like Resitech or Uyghur, Safer Places, Forland, the Landscape Finance Lab, and so on. So what I wanted to focus on this morning is, as a practitioner in the climate adaptation innovation space, and if you'll excuse the pun, using space data, what have we learned and what do we see in terms of the climate services market and the opportunity for European innovation to address the needs here and to bring together the supply of climate services and the supply of information and decision support together with demand, because that's probably the area that we see as being most critical as we look forward towards the mission and the implementation of the adaptation strategy within European and global contexts. We still see that there is a very immature market in terms of climate services and the need for that. 90% of the companies that have been impacted by climate-related events in the last 4 years, only 30% of those organizations responded to those threats. We see the market growing by about 8% per year, but it's still relatively immature, and in particular, demand is largely latent. It's very hard to work out where climate services are being actively used and not, in part also because the knowledge varies dramatically across sectors and users. And many of the organizations and individuals we're working with are not necessarily easily able to say whether they're using climate smart information, climate services, or space data or not. And some of the reasons for that have to do with imprecision in the data or inability to access reliable data, where climate innovation is perhaps not considered as relevant as other elements, or where climate issues are not considered as high a priority as others, or just a lack of awareness that climate information can be used. So we see that there are problems in terms of, also in a European context, the strengths that we have in a European context are favourable legislation. They are policy that has precise targets at EU level. One of the challenges is a lack of synergy and coordination, however, between member state policies and at the member state level, and how to address that dislocation between a European-wide arena and the way in which that translates into coherence right through to national, subnational level, particularly where it's most needed at regional level and city level. We see that there is a massive acceleration in the development of shared codes and standards, and we're seeing that also in the startups and new businesses that we're supporting. What is and would be enormously helpful is more coordination and cooperation between EU initiatives to further accelerate, encourage and support that and connect it down to subnational level. And there's also a very strong global outlook in terms of a European area of excellence. This is an area of significant opportunity and excellence. It probably and does need more commercial funding coming in, an investment focus that begins to understand the significance of both what is needed and what is possible. So in terms of some of the most kind of specific and granular learnings, we know that detail on intensity, on frequency, and on spatial distribution of climate hazards at a local level is still very uncertain and kind of uneven. Information about social and economic vulnerabilities is just as important for adaptation innovation and for adaptation decision making. In low-income countries, however, that information is often missing, and this is one of the challenges of the last mile that I'll come to. One of the things we see is the absolutely essential need to have as a design principle in this whole area the involvement of local communities, of people who need to use climate information, of business owners, small and medium businesses, so that they are part of the process of generating the information itself, but also generating the solution space and the decision support tools. Knowledge about adaptation solutions is just as important as information about risks and vulnerabilities and impacts. And this is an area where there's quite a bit more work to be done, because that knowledge exists in a formal level, but it isn't kind of declining necessarily down to where it needs to at local levels. We see the importance of peer-to-peer exchange and building up repositories of information that are accessible to participatory engagement and dialogue. And investments, really the importance of channeling investments into supporting the use of information in decision-making, not only, and that's an area where investments are really lagging behind, not only in the generation of awareness and understanding and connecting climate science to climate risks and hazards, but really also then pulling in support for the use of information in decision-making and connecting to adaptation solutions. And that brings me really to this question of the last mile. And I framed for myself the kind of shift from considering a possibility of shifting from the last mile to the first mile. And that really refers to the fact that there is a critically important shift here that needs to happen to bring together what is still fundamentally a supply-driven market in climate services and climate adaptation solutions into strong and deep connection with demand, and a much more explicit, well-informed, well-supported relationship with demand. And by demand, I mean city governments, regional governments, local communities needing to access and use real-time information and real-time solutions. So one of the things that we see, as if I describe it in sort of structural terms, is to shift from a hazard by hazard risk reduction practices to much more systemic approaches in both understanding the risk, in real-time assessments of that risk, and most importantly, in responses. So we get to a state where people and communities and systems are able to withstand and bounce back from climate shocks and persist through slow onset stresses, which is one of the major issues we are facing and will face more and more, so that they can use this information and the connection with solutions and decision support and real-time delivery to transform and prevent. And that's really, I think, the principal priority, certainly for an organization like EIT Climate-KIC, of the focus of our innovation efforts, to focus on adaptation solutions that are and perimeters that are systemic, working through a portfolio approach of bringing together multiple demand-driven options to engage climate science to support decisions in the moment and to design transformative alternatives and responses and adaptation solutions with communities. So in a peer-to-peer logic that brings together clusters of active and connected networks working on regional resilience, feeds the information and experience from that through to policy and regulation so that we get resilience-focused policies and action plans that also acknowledge and incorporate slow onset changes as well as extreme events and systemic risks. A much more explicit focus on community engagement and empowerment for a socially fair set of transitions. And a lot of the innovations we're seeking to support are offering solutions in that space. And as I said, the investment element, rebooting and structuring in regional growth through long-term investments that are seeking an opportunity space in resiliency and in resilient building, business building, community building, future of work building, and territorial regeneration and renewal. And this is very much about stewarding and regenerating natural capital and livable places. I think the mission really opens up a frame for doing that. It sets a scene and an invitation to think in those terms, to think systemically, to bring demand and supply firmly together into a co-design relationship. And the adaptation strategy provides the policy framework for that being understood as one of the key structural elements of the way in which we address climate change, and not as an incidental kind of later stage response, but really actively an active structural way in which we address mitigation and adaptation together and seek to encourage the flows and transfers of ideation and of solutions backwards and forwards between them. Thank you very much.
Thank you, Kirsten. Thank you so much. And now we have ready Philippe Tulkens. We want so much to work with technology, and technology betrayed you. Philippe Tulkens is our keynote speaker. Since early this year, Philippe is the action head of unit Climate and Planetary Boundaries in the Research and Innovation Director General of the European Commission. He worked as deputy head of unit on accelerating clean energy innovation in the context of the Energy Union, and has a policy assistant to the deputy Directorate General of DG Research and Innovation. Finally, we were expecting you, Philippe. Hi.
Yeah, thank you for your kind introduction. I hope you hear me, and I apologize for these technical problems. Do you hear me?
Yes, Philippe.
Okay, thank you. Apologies for this technical problem. We did a test, everything worked well, but this word is highly unpredictable. And from one day to the next one, there are some changes, perhaps in the system. I think we still have a lot to do in Europe on standardization of systems, because each time we use a new system, we have new problems. Anyway, but Kirsten opened the session, and she speaks much better than me, so I'm sure she delivered all the key messages. I just heard a few words about the mission. Kirsten, do you hear me? Because I see that you seem to indicate that you can't hear. Excuse me. If you could just nod if you hear me, or say whether the sound is kind of synchronized with the image. It doesn't seem the case. And I see from Kirsten that...
Well, I'm not hearing you, but I think the audience is. I'm asking the director. Yes, the audience is hearing you, yes. No? Well, but the other speakers aren't, right? So we have a problem here with Philippe, because our speakers are saying that they can hear him. The speakers can't hear them. Yes, they're telling us that they cannot hear Philippe. Philippe, can you talk again, please?
Yeah, I can try.
I'm listening to you right now. Okay, the other speakers are telling me with the hands that they're now listening to you. Finally, what an audio problem we had. Now everything's okay, Philippe.
Should I speak?
Yes.
Apologies. So
no problem. Blame technology.
You see that the challenges of standardization are still big, and I was saying that Kirsten speaks much better than me, so I'm sure she passed all the key messages that I wish to pass, and that they come across better. So I will, if that's okay, if I continue.
Yes. Perfectly.
Thank you. Okay. So, challenging times for communicating. We see all these technologies delivering marvels, but also some basic difficulties. I will try to shorten also my interventions, because we are getting late. And thank you for the invitation to this conference. So I'm acting head of unit in the European Commission, working on climate and planetary boundaries. And in the context of climate activities, of course, the research and innovation has a key role to play, and does play a key role. And the key messages for this speech is that the focus on adaptation is now increasing greatly. I understand that Kirsten Dunlop referred to that through the adaptation strategy adopted recently by the European Commission and through the mission on adaptation to climate change. As you know, with regard to mitigation, the trends and projections in Europe 2020 report by the European Environment Agency show that we are well on track and reach our 2020 target. I think it's very important to recall this because often we look only at the future and don't see the achievement of the past. It's not sufficient, but it's a good progress. But we know that we have to increase and go further and faster. And you also know that the 2030 targets have been made more stringent and greater. And you also perhaps have heard that yesterday there was an agreement early in the morning on the climate law. So the climate law defines the objective for 2050, but also reinforced objective for 2030 now. And this is a key decision that we need to implement. And research innovation will have to play a key role in that. The European Commission will have to propose a number, around 50 legislative proposals to achieve the updated climate target. So we are frantically working towards delivering on this ambition and acceleration. So the research community is at the source of producing the knowledge that is indispensable for developing innovative solutions. Should I continue? Because I hear a lot of conversation through my phone.
So I'm going to ask that they can turn off the sound from our room. Yes, sorry about that.
I will do my best. Okay. So we need to further strengthen our efforts on the development of the knowledge, and this is what Horizon Europe, the European Programme for Research Innovation, is doing. As I said, the key message for this speech is to refer to the mission on adaptation to climate change and the other Green Deal missions, because that's what is absorbing much of our energy now, and that is also what is new. The research will go on. The efforts to promote and to develop solutions will increase. But what we need to do is to test these solutions and deploy them faster and better in Europe. 4 of the 5 missions proposed will be extensively using data and services provided by EU space programs to ensure that they reach their set objectives. And so will be the case for the mission on adaptation to climate change, including societal transformation. The mission seeks to speed up the preparation to make Europe climate resilient through the demonstrations at scale of best available solutions. So typically what the Climate-KIC is doing, but at a wider scale, bigger and faster, and with them also, for sure. To do this, we need first, of course, to further improve the understanding of climate risk and provide access to climate risk assessment, built upon cutting-edge climate and environmental information from European Earth Observation Programme. This access to the information is key. This is what we hear from the stakeholders we talk to. The mission has 3 objectives. 1, to better prepare Europe to manage climate risk. Number 2, supporting up to 200 communities and regions in their design of a vision for innovative pathways and testing innovative solutions with them. And third, upscaling innovative solutions and implementing up to 100 climate resilience deep demonstrations. So that's the overall ambition. Now the Commission, this ambition was proposed by a board of experts called the Mission Board, chaired by Connie Hedegaard, a well-known actor in climate policies at European level. And now the Commission is reflecting on the concrete implementation plan. A decision will be taken on the implementation plan for the mission late June, early July. And once the decision will be taken. If it's positive, it will be not a big bang, but a very significant investment into these applied activities through the mission. But yes, with regard to now Earth observation programs, I should say a few things. Of course, we know that they are very important in gaining better understanding of the risk involved through climate change. But we know that in the next decade, Europe will rely on the most comprehensive and sophisticated space-based observation infrastructure in the world, including an extraordinary and complementary suite of sensors on board of Copernicus Sentinel series, the ESA Earth Explorers, the coming meteorological missions, and different Earth observation satellites planned to be launched by national space agencies and private operators in Europe. We are not starting from scratch. We all know that. Significant improvements have been achieved in weather prediction over the past decade, due in large part to a larger international fleet of improved meteorological satellites and also better modeling. Many of the essential climate variables, the ECVs, identified by the UN Framework Convention on Climate Change, depend on satellite information. In terms of observation, the Copernicus Climate Change Service, C3S, already provides access to 22 of the 54 essential climate variables. A preliminary analysis made by our colleagues from the European Centre for Medium Range Weather Forecast, ECMWF, suggests that it would be possible to increase the C3S portfolio of Europe's essential climate variables by 13 to reach a total of 35 ECV. Satellites contribute to the understanding of the global water cycle and to improve freshwater management. Clouds, water vapor, precipitation, and sea levels are all measured from space in coordination with in-situ systems, and the in-situ systems are also fundamental to complement satellite data. Satellite data can also support assessment of progress in adaptation by monitoring changes on Earth's surface, such as forestation, changes in the disaster impact, evolution of urban areas, and so forth. EU-funded results achieved through the analysis of satellite data provide significant information to the IPCC assessment via peer-reviewed literature on the use of satellite data and products. And as you know, this summer, the IPCC will adopt the Working Group 1 report on the climate and the physical basis of climate change, the update in the current assessment cycle. This will be an important moment to take stock of the progress that science made also through the observation part that you are all active in. Ensuring that the scientific community takes full advantage from this unique opportunity and maximize its scientific and societal impact is urgent and will require a significant collaborative effort and an integrated approach to science, where the synergistic use of Earth observation, satellite data, in situ, and citizen observation, advanced modeling capabilities, interdisciplinary research, and new technologies will be essential elements. Via its engagement in a group of Earth observation, the European Commission contributes to the international community effort to inform the climate and mitigation process. This year, the EU, through the EC, is lead co-chair of GEO, as you may have heard from Patrick's side, who is leading the EC delegation there. And we will be enabling and promoting access to the use of Earth observation in responding to and monitoring progress for the climate transition. There are, however, still gaps in Earth observation coverage that sometimes limit the adequacy of the sensors available. Together with the gathering of data through environmental observation, there needs to be harmonization of the existing data and the one collected to enable effective monitoring of progress of the adaptation pathways towards the set target. Data integration into larger information systems can also be complex and time-consuming, especially for real-time application. Reaching the regional and local levels with usable data and fit-for-purpose climate services to support the ambitious objective assigned to the mission remains challenging. This is a key element to reach really the end users, be it the citizens, the local authorities. Local adaptation strategies need tailored information on climate and impact at local scale and ranging over timescales from seasons, years to decades, up to centuries where possible, under different emission scenarios. Really, the authorities need the best available science provided in understandable through tools that are understandable to them. Services need to be usable by non-experts. This is what I meant to say, including citizens, where the commercial sector can play a strong role developing business models for climate services. The ultimate goal is for each actor to be informed and empowered to make decisions and act to address risks and impact that may affect their neighborhood, their business, their farm, and so on. To conclude, to assist citizens, communities, and regions in better understanding, preparing for management, the management of climate risk. So the first objective of the mission and the mission targets are as follows. All local administrative units and regions need to have access to climate risk profiles and enhanced early warning systems for relevant risks. They will have to adopt comprehensive climate risk management plans. They will have community infrastructure and services that are safe, operable, and accessible under critical conditions. Earth observation and space technology have a unique opportunity to contribute to the mission and can provide elements of answer to all of the above mentioned mission targets. The European Commission Research and Innovation Programme, the European Union Research and Innovation Programme, together with other EU programs such as Copernicus and Digital Europe, stand ready to assist the Earth observation industry in engaging further evolution from a data-driven industry towards becoming a knowledge generator. And I hope that the users would be satisfied. Thank you, and please apologies again for the difficult condition of this speech. I hope the message could come across nevertheless. Thank you.
Thank you, Philippe. No reasons to apologize. These things happen, unfortunately. And we are so distant in all over the world, so telecommunications probably didn't help, of course. It's normal. Thank you so much, Philippe. We carry on with this conference and with this sharing of experiences and knowledge, and now with Nuno Carvalhais, scientist at Max Planck Institute of Biogeochemistry, PhD in Environmental Engineering from the New University of Lisbon, Nova. He is leading the Model Data Integration Research Group in the Max Planck Institute for Biogeochemistry since 2012. Hello, Nuno.
Hello. Thank you very much.
Welcome.
Thank you. I would like to start by thanking for the invitation to be here. I'm very honored. And one of the things that actually happened was that immediately an idea resonated that speaks about insight must precede application, something that Max Planck said many years ago. And and when I started putting this talk together, one of the things that came to mind that I think is important to fundament is that the understanding of what happens in ecosystems at very short timescales also propagates to longer timescales. So it actually means that what happens to instantaneous meteorological events during seasons and during years propagates into the way that ecosystems develop and into their aspects that contribute to their own resilience or vulnerability to conditions that are similar to the ones of today, but also to conditions that are very different from those. And the way that today we try to learn how all these different processes that go from the scales of seconds and minutes to years, decades, and centuries, but also from the molecular level or the leaf level to the whole plant or tree level, at the landscape, at the whole continent, and to the globe. It comes from actually bringing together what we harvest from observations and that we can synthesize into theory, knowledge and integrate into models that then make this direct interaction between different cycles of energy and mass. And that's the way that we describe how current ecosystems function today, but will also function in the future. And observations are fundamental aspects of deriving information to build knowledge. And we have been through, not only in the last decade or 2 decades, we've been like for at least 100 years, we've been looking into networks that were not thought as networks in this way, but that were measuring things like leaf phenology, that were measuring things like the mass of trees. And we've been building all this knowledge about ecosystems from networks that are very sparse and very local into a reality that started maybe in the late 70s, early 80s, that actually measured these in many parts of the world, like completely wall-to-wall distributed and ubiquitous source of information. And this has been fundamental for us to understand how biogeochemical cycles that control life on Earth are operating from very small to very long timescales and spaces. And when I speak about this, I'm speaking about something that we can formalize in a very simple way here, that what we're talking about is about how ecosystems that harvest carbon out of the atmosphere via photosynthesis and then distribute that carbon through their different plant organs that then transfer it to the soil, also respire it back into the atmosphere. And there is a very, very sensitive balance between these two fluxes that basically control how current human emissions can be amplified or dampened by what is currently natural ecosystems. And the way that we have to learn about this is by having measurements of how carbon and water interact at the plant level, at the soil level, and how they are mediated by environmental conditions and meteorological aspects like temperature, precipitation, and soil moisture, and radiation. And through time, what we have been learning is putting together what Philippe mentioned also, like in situ networks with Earth observation in many of these locations spread all over the world. And by doing that, we've been getting insights into how photosynthesis and assimilation of carbon and plant activity is sensitive to short variations in temperature, in water availability, and how these sensitivities are changing in different ecosystems, like how tropical ecosystems are different from Mediterranean ones, temperate are different from boreal. And these reflect not only local adaptations through very long timescales, but also the fact that the local conditions are different. And Earth observation is key to understanding how these local conditions are changing in space in a very continuous way, in a way that we can understand better the mechanisms that control changes, but also try to quantify them as best as possible. And this refers not only to the vegetation part of an ecosystem, but also to the soils and to decomposition, because these are very sensitive to things like temperature and water availability. There are places in the world, like northern latitudes, that have been locking a great amount of carbon in the last millennia, given their constraints by temperature, and that we don't know how they will react in the future, and if this unlocking would actually amplify the current emission scenarios that we predict into the future. And when we talk about prediction, there are challenges that we have that are posed, that are from a conceptual point of view, very important. So will a tree, will an ecosystem that is answering today to a current meteorological condition function in the same way in 50 years? We don't know this answer. There is this aspect that by having a change in mean temperature, having a change also in species composition of different ecosystems, the behavior may reflect a resilience via adaptation, or may reflect a vulnerability by lack of it. And we have models that try to simulate this. We conduct experiments in particular parts of ecosystems via manipulation of different factors in order to understand this. But this is actually conceptual challenge that we have in understanding and quantifying how much it could be, so that we can derive better forecasting of or better prediction of how future scenarios will change the current way that we see how ecosystems function. The other aspects that relate to this fact of adaptation refers to the sensitivity of current ecosystems to things like mortality and recovery from mortality, and mortality coming from extreme events of drought or heat or of fire or of things like wind blows. How fast is an ecosystem likely to recover in present conditions and in future conditions? And in first order, so meaning that when models try to predict if there is an increase or reduction of biomass, like we see here on the left, when you go into the future, they actually agree in terms of the direction most of the times, but how that reflects sensitivities to gain versus loss of carbon, or meaning like mortality versus assimilation, they usually don't tend to work. They tend to not fully agree with each other. And that doesn't reflect that we don't know everything that is going on, but reflects that if we want to do a better predictions long term, we really have to understand what controls and be able to quantify these fine balances between losses and gains. And Earth observation puts a great opportunity to do this at long timescales, so meaning that we put already, like Philippe was mentioning, observations of climate, like for instance precipitation on the left, with measurements of vegetation activity, like the one that we see on the left, on the center, during the last 30 years, to actually have a picture of how biomass and current forests look like today, like we see on the right. And we can do this looking at global patterns, very wide patterns all over the world, but we can also zoom in into particular aspects of load and try to understand these temporal sensitivities. And this is where it becomes like mostly important to not only look at the current deluge of data that is coming with Copernicus and other missions, but also look and cherish the information content that has from legacy data that started already in the 80s and some even before. Because it is in this information that we understand how time and how variations in climate have been imposing new boundary conditions, new conditions into ecosystems, and how they have been reacting to that into a way that emerges to the current contemporaneous observation of biomass and other ecosystem properties. So when we think about the opportunities that come from Earth observation, indeed, this plethora of data sets that are coming are fundamental to evaluate the present models, like from the local ones to global Earth system models, but also to build new ones, given that we can test more hypotheses, we can actually use novel machine learning approaches, statistical approaches that are associated, for instance, to artificial intelligence, to understand better sensitivities within the process that we're simulating in models, and that emerge into these big patterns of biomass, of vegetation activity. Sorry. And to this end, and picking a bit on what yesterday was said by Dr. Gregory Jenkins, one important aspect, if we really truly want that knowledge is a democratic and ubiquitous exercise all over the world, this data needs to be free, needs to be accessible and open, as it is being done today, which is very nice. And at the same time, the tools to use this data is also very important that they are made open, that they support capacity building. They have to be transparent. We need to know what these measurements actually mean. It's not usually straightforward. And the quantification of how confident we are in the data is very important to understand how we're evaluating our models. What are the strong components of the models and which are the ones that we have to work on? I think that given that in today already and in the near future even more, these data sets are going to be used for decision taking. We as data producers, as people that also try to synthesize information into knowledge, we need to embed the responsibility of the confidence that we have in this observation and the responsibility to inform on the meaning of these measurements, on the meaning of our conclusions. And this is something that I think it's very important for us to engage, as Elena was saying yesterday, in speaking out well to the public in general and decision takers in particular. I would like to finish and to synthesize this idea that the new data is amazing and the historical data is fundamental. That Earth observation is a ubiquitous and unprecedented data set, but data sets that have been there already from ground networks are fundamental for deriving understanding, and especially in a period where statistical models that can be very opaque need to be interpretable. The ability to actually use ground data and in situ observations to do process understanding and interpretation of links is fundamental to actually support this. One thing that I believe Earth observation is unique at is into respecting or observing the cautionary principle. I think aspects of conservation, monitoring of conservation, diagnosing recovery strategies or recovery patterns that come out of restoration strategies, alongside with coordination with networks that allow us to understand how the processes are being changed in a context of a non-stationary climate. This is fundamental for us to be able to do diagnosis currently, but also to be confident about the way that we predict the future, especially the near future. Thank you very much. I look forward to the next talks as well.
Thank you, Nuno. And thank you also for this double exclamation. Don't forget the soils that you had on display. Thank you so much. Very interesting, the opportunities of learning Earth system and to use that through the observational networks. Thank you so much. We're a little bit delayed, so let's go for it. Now it's time to hear Celeste Pereira, but I also remember that someone or everybody actually that have questions to do, any doubts about these presentations, can expose their questions in our chat box. It's just go there, use it, because it's from this conversation that we can explain things and find solutions. Now, Celeste Pereira, PhD in chemical engineering in 2002 and did a postdoc in mechanical engineering. She has several years of experience in the development of business and technology in the space market and especially space hardware. Well, is space hardware taking care of our planet, Celeste? Hello.
Hello. Good morning.
Good morning.
Okay. Thank you for the invitation and thank you for the opportunity to be here and to present the perspective of the developers and the manufacturers of space hardware and how this hardware and our work is contributing for the protection of our planet. So, okay, if I achieve, sorry. Okay, so for us, the space hardware manufacturers and developers, space is okay, there is no presentation, is a hard vacuum with very harsh conditions where there is there is cosmic particles. I have a problem with my presentation. Sorry. Okay, there is hard vacuum that contains a low density of particles that has electromagnetic radiation. There is magnetic fields and cosmic rays and many other particles or elements that are challenging for the spacecraft hardware, and also the baseline temperature in space is minus 270 degrees that we have to take into account when developing these machines. Space hardware, and just briefly, as you may know, are satellites, are the spacecrafts like ExoMars 2006 in TGO that is orbiting Mars. There is also the launchers that are needed to put these hardware in space. There is also the spaceports with all the launch pods and assembly rooms there to put all these space hardware in space. And important also is to highlight to manufacture and assemble these hardware. We need special facilities for manufacturing and assembly. This hardware is taking care of our planet, as Nuno showed before, by the data that is collected from information of the cycle of the CO2 and many other aspects. And here I just briefly made an overview of, for example, what is being done by the Copernicus Sentinel missions, that is the maritime monitoring, land monitoring, atmosphere monitoring, and also contributed on the emergency management, on security management, and also as to understand the climate change. On maritime monitoring, there is ice monitoring, ships monitoring, oil pollution monitoring, and many other aspects of the oceans monitoring. On land monitoring, there is satellites collecting data that are helping us to risk mapping, for forest monitoring, desertification monitoring, and also supporting us on emergency management, as here in this slide, an aspect of the ongoing fires on Chernobyl area in 2020, and the data collected from satellite supported emergency teams. Also on the climate change, how the sea level are evolving along the years. Another perspective of this hardware is taking care of our planet is also on the avoidance of the asteroids impact. There is an example of this ERA mission that is together with a DART mission from NASA that are studying the possibility of deflection of asteroids, and thus to avoid the impact with Earth. Sorry. Another aspect of how this space hardware is taking care of our planet is on these amazing machines that are being developed today for cleaning the space debris. Today, there is already several satellites in hand life orbiting Earth, and this is clear. We have to remove them from there, and with this avoid debris and any possible damages. This hardware is made by many engineers, multidisciplinary teams all around the world. Normally, the teams that made this or design and manufacture this hardware are multicultural, multi-country, multi-company level. So there is always a teamwork behind, and normally engineers design the space hardware with a purpose that is the need for a mission that is usually defined by scientists like Nuno and others, and then the engineers, the space hardware engineers, have to find a way to put all these instruments and all these equipments in a structure that go to space and then still be functioning in space. even when in space we have these very harsh conditions. Sometimes when a mission is identified is also at that moment that starts the need of developing some certain technologies, because the conditions of operation of these machines are very harsh, and there is the need for additional research and developments. Another two pictures of ExoMars 2016 during the assembly and also preparing for being integrated inside of the launcher. This mission I had the opportunity to be involved, and it's really important here to highlight that all this work is done by skilled people with very large qualifications, and important also the means, the facilities where these satellites are assembled. There is an agreement that when we send a spacecraft to another planet, we have to assure that there is no biological contamination, so we have to manufacture these hardware in very cleaning conditions. Another type of hardware is an example is Vega launcher here in the launch pod, and then the exploded view where we can see the different stages with the different subsystems for propulsion and also for the containment of the satellite and the fairings that protect the satellite. And two pictures of this structure or the elements of this launcher being made. For this space hardware, there is several building blocks. There is complex metallic parts that are needed for these launchers and satellites. There is also the need of these kind of sandwich panels that are based on carbon fiber reinforced polymers, and these structures are also used either for satellites and also for launcher fairings. And the basic materials or raw materials for these building blocks are either metals for the metallic parts, but also for these composite materials are the carbon fibers, the polymers, the SME products that are made with these two basic raw materials, and then they are manufacturing with very advanced manufacturing process. There is a lot of chemical engineering reactions there, so there is multidisciplinary activities behind these building blocks. These composite materials are also used in other areas of application, are also used in Earth and terrestrial applications. Composite materials are light and strong structures, and they allow the manufacturing of large wind blades or aircrafts. And these structures allow the reduction of vehicles consumption, and this is very important for the increasing of the electrical vehicles autonomy, or to reduce the emissions of air pollutants when they work or they function with the fuel. Important is also here to highlight that composite materials have a very clear technology roadmap for sustainability. All the developers and manufacturers all around the world of these space hardware, but also terrestrial hardware with these materials are developing research for waste reduction, trying to recycle these materials, and also to use green-based materials for manufacturing these structures, either by using natural fibers, bio-based polymers, and also very recent is on the carbon capture and utilization of CO2 and conversion for the basic chemicals that are used for the raw materials that are used on composite materials like the carbon fibers and the polymers. important here, I just highlight here is what we are doing at my company at Optimal. We are doing research and development in different fields of this space hardware that are either on satellite structures, on composite pressure vessels, on these launcher fairings, but also on large mechanical equipments. And it's also important that all the work we do on development for space hardware, it can also be transferred for other applications and terrestrial applications, and it's that we are also doing in our company. So this is my last slide, and I will conclude my presentation. But important is I will leave this message that this hardware, space hardware, is protecting our planet in its several dimensions, and this is real crucial for the adaptation and mitigation of to the climate changes. Thank you.
Thank you so much, Celeste. So the satellites are, in fact, the big brother. So I see. Thank you so much. With no further delay, now Ricardo Galvão. He's a professor at São Paulo University, Brazil, obtained a doctoral degree in applied plasma physics from the Massachusetts Institute of Technology, known as MIT. He is specialized in nuclear fusion research. Hello, Ricardo. You have something to say to us about proposal for an internationally coordinated system for satellite monitoring of major forests. Welcome.
Yes, thank you very much for the invitation. I will start with my first slide immediately. Let me see if I can see it.
Yes, perfectly.
Are you seeing it? That's I don't see it here. Oh, the first one. Okay. Well, I would like to share with you today some ideas about implementing international system for monitoring major forests. What you see in the background is a picture of the DETER system developed by the Brazilian National Institute for Space Research to provide daily warnings of deforestation and forest degradation in the Amazon rainforest. This system has been quite effectively used by the Brazilian Minister of Environment to reduce deforestation in the Amazon from over 27,000 square kilometers in 2004 to slightly over 4,000 square kilometers in 2012. But as you all know, unfortunately, deforestation in the Amazon rainforest is picking up again. So I'll move to the next slide. I'm not sure if I move it here or you move there. I'm a bit confused about that. But anyway, let's go to the next slide. We all know the role of forest for carbon sequestration. And actually, 31%, almost 31% of the global land area is covered by forests, but not evenly distributed. 5 countries, the Russian Federation, Brazil, Canada, United States, and China, have over 51% of the forests. 10 countries have around 66% of the forest. In spite of that, for many decades, the only system we have for keeping inventory of the forest is that one developed by the Food and Agriculture Organization of the United Nations. This inventory is based upon reports provided by different nations, but not in a very well organized way and in a systematic format. So it has been recognized in the last 5 or so years that for establishing effective global policies to reduce emissions from deforestation, forest degradation, the so-called REDD+, we need an international coordinated forest monitoring system. Why forests? Next slide. Well, the estimated forest stock of carbon is around 860 gigatons of carbon. 55% is in tropical forests, 32% in boreal forests, and 14% in temperate forests. In particular, primary forests are very important because they have higher carbon stocks, not only in the trees, but also in disturbed soil, as Nuno said, and also in the pit. Well, we all know that to limit the global warming, that the average global temperature to less than 2 degrees centigrade by the end of the century, we need to keep the concentration of carbon dioxide and other greenhouse gases in carbon dioxide equivalent to less than 450 parts per million. Well, we have already reached 400 parts per million. And we know that we have to take many measures, as has been said in this conference, to reduce the emission of greenhouse gases by industry, by transportations, and many other means. However, if we do all that, but we let the forest go, then we are in trouble because of this carbon stock. If we lose all the forests by 2011, by the end of the century, would emit carbon dioxide, the emission should be equivalent to 50 to 100 parts per million, increasing. So that would surpass this limit that we have to respect. Actually, a halt to deforestation and forest degradation would reduce emissions by 1.4 gigatons of carbon per year. And if we allow then for reforestation, then would increase from 1 to 3 gigatons of carbon, the intake of CO2 from the atmosphere. So we definitely need a well-coordinated, effective, comprehensive, and properly supervised scheme to monitor deforestation and forest degradation. And here is very important, with fast enough response to allow swift actions by international organisms. Well, and you all know we have for system is through imagery. Actually, sensing forests by satellites began in 1972 with the launch of Landsat. The relevant techniques have immensely advanced since then, as has already been said in this conference, using both passive, mostly optical, and active radar and LiDAR sensors, and also cutting-edge methods of image processing. Currently, we have over 700 active non-military Earth observation satellites in the Earth. 75% of them were launched last year, within the past 5 years. These satellites are available. So regarding satellites too, we have plenty to implement such a system. One problem, however, is image processing and data storage. Actually, forest monitoring by satellites is employed by many countries and institutions, as we all know, but still not in an integrated and internationally coordinated arrangement. And that's our problem. So what I would like to suggest today is that international coordinated system for satellite monitor measure forests be implemented. These go along the ideas put forward by Jimmy Lynch and collaborators in a very nice paper in Nature in 2013. This international system should not only provide reliable and open data on annual deforestation and forest degradation, but also implement an early warning mechanism along the lines of the Brazilian system PRODES and DETER, which are well recognized worldwide as one of the best systems for monitoring tropical deforestation and forest degradation in tropical forests. I'm in the last slide, and those of you who want to see more about the system can access the site given this last slide. Well, important that this system, to start with, could be based mostly on medium resolution large SWOT sensors, like those of Landsat 5, which has a resolution of 30 meters and SWOT width of around 108 kilometers, and use artificial intelligence, machine learning, for data processing. But those automatic systems for image processing, they have reliable image calibration and, most importantly, expert validation of the critical data and high capacity of data storage. And also, I believe that we need a modern constellation of equatorial orbit satellites to increase the frequency of revisiting the tropical areas. I believe that the most effective way to implement this system seems to be through a dedicated international institution with delegation from the United Nations. Thank you very much for your attention.
Thank you so much for this. We are very delayed, about 15 minutes. So if we have no questions from our audience, so probably we have to skip this part because it's starting to be very late and we have so many things to do and to hear, and someone has to go for it and to finish this first panel. I have to thank you so much to our speakers, and I'm going to invite you all for a coffee break. Well, a different coffee break because we are so distant and we can mingle. That's unfortunately the problem. We have to deal with it, not only for the pandemic situation, but because you're very far away from Portugal, most of you. So I invite all the audience for a coffee break, and I remind something, that the first 100 registrations that we had at this conference received a small gift. Well, not so small, because I've seen it, a box with so many things to enjoy to this coffee break. A box with Portuguese delicatessen. So probably is the best thing to do now is to enjoy this coffee break. The first 100 have a privilege, so we may say, and we'll return in a short break. See you then.